Hello and welcome back to my channel. Today we'll be talking about power. So what is power? Well, power, it may not be like the power you may used to be hearing, like you have power and strength, or I have a lot of power today. Power in physics refers to the rate at which energy is transferred. So the rate at which energy is transferred. What is the equation for power? Well, the equation we use for power is P, which is the symbol for power, is equal to the work over delta T. And remember, work is also equal to delta E over delta T. So these are the two equations we can have for power. We can have power is equal to work over delta T, or we can have power is equal to delta E over delta T. So now that we have this, we also have a new unit for power, and the units we use for power are joules per second, which is equal to a watt. And the symbol for it is just W. So now that we have this, we can move into doing some questions and seeing the applications of how we can use power throughout this course. So let's look at this first question. So let's get our given now. How much power does a swimmer have if she transforms 2.4 kilojoules of mechanical energy into kinetic energy and then thermal energy in 12.5 seconds? So it says she produces 2.4 kilojoules of mechanical energy into kinetic and thermal energy. So that basically is just talking about what our energy is, which is 2.4 kilojoules. And remember, we should probably just convert this into straight up joules just to keep everything a little more simple. So we have 2,400 joules. And we have our delta T, which is equal to 12.5 seconds. So now we can go into our solution. We can go into our required to find, which is, it's asking for how much power. So we're looking for P. We can go into our analysis. We know P is equal to, again, we can look at our formula, delta E over delta T. From here, everything's already done for us, so we can go into our solution. P is equal to 2,400 joules divided by 12.5 seconds. P is equal to 2,400 divided by 12.5, which gives us 192 watts, because joules divided by second is watts. So we have 192 watts, and two significant digits we'll get, because we have two significant digits here, we should keep two significant digits, we get 190 watts as our final answer. Now let's look at the next question. It says, a 64 kilogram student climbs from the ground floor to the second floor of his school in 5.5 seconds. The second floor is 3.7 meters above the ground. What is the student's power? So we can go the mass of the student, which is equal to 64 kilograms. And he climbs the school in a time of delta T. Delta T equaling 5.5 seconds. So now we have that. We know he climbs a distance of delta D, or of 3.7 meters. This can also be the height that he climbs of 3.7 meters. So these are both really equal to each other. It doesn't really matter what you label them, as long as you understand that they are equal to each other, and they can be applicable in both ways, right? So now that we understand that, we can look at what we are required to find this. Well, actually, we can also go ahead and just write the constant of gravity, which is always just G is equal to 9.80 meters per second squared, and go into our required to find, which says what is the power. So this time you'll notice that we're not actually straight up given power, but rather we're given some information that can maybe help us find what power is. So how are we going to do this? Well, we can write the equation for power. Delta E is equal to P is equal to delta E over delta T. So what is delta E in this case? Well, there's no mention of any kinetic energy, just about a student moving from the second floor, from the ground floor, to the second floor. So because we know that there's no really moving kinetic energy, we can assume that his energy is actually all Eg, or gravitational potential. And we know that delta Eg is equal to Eg2 minus Eg1. And because he does displace 3.7 meters, but this is his height too. And this is technically, now that we know that we're going to be working with gravitational, we can go into height straight away. So now instead of writing delta D, we can go H2 is equal to 3.7 meters. And assuming that he was on the ground floor right here, if he was right here to begin with, the ground floor will be 0 when he's up here. His new height is 3.7 meters. So H1 is just equal to 0 because it says he climbs from the ground floor to the second floor. So he's starting at the ground. So now that we know this, our Eg1 will drop out because our height 1 is 0. And now we know delta Eg is equal to Eg2. And this is all equal to delta E, which is his total energy. Now, if we want, we can sub this into here. We can label this as 1. We can label this as 2. We can go 1 into 2. And we can just sub it in. So we know P is equal to mgh over delta T. And now we can jump into our solution. So our solution will be analysis. Pardon me. Our solution will just be P is equal to the mass, which is 64 kilograms, I believe. Yes, 64 kilograms multiplied by 9.80 meters per second squared, multiply the height, which is 3.7 meters. And if you remembered, all of this ends up being, we had kilogram times meter per second, times second squared, which ends up being a joule, and we'll have on the bottom time, which ends up being 5.5 seconds. And all of this will end up being a watt. So power is just equal to, now we can go ahead and find what the power will be. It's 64 times 9.8 times 3.7 divided by 5.5, which ends up giving you 421.93. There's two significant digits here, so we should round to two significant digits. Our power is equal to 420 watts. So that's your final answer for this. And that's basically just the first section of how we can use power with energy. The next part we're going to talk about is electrical power and how that's really used in our physics unit. Okay, now we're going to be looking at electrical power. Well, what is electrical power? Electrical power is basically just power, but in electronic devices. So what is a term that we use in electrical power that we often use is a power rating. Maybe oftentimes you'll see this on your charging watts or throughout your laptops or electronic devices. What is a power rating? Well, a power rating is the maximum power of an electrical device. So the maximum power of your electrical device. And something you'll notice that sometimes you'll have a 5-watt brick, a 10-watt brick. Well, all of these terms are electrical power, are forms of power that we see in our everyday lives. And all our really our electronic devices do have a power rating, and this is used all throughout the world. So a formula that we can use here, or that we might need to use, is delta E is equal to P times delta T. And how do we get this formula? Well, if you remember our old formula for power, well, delta E times delta T. If you want to rearrange to get delta E, we just multiply by delta T, and power times time is equal to our energy. Why is this important? Well, because when we're working in electrical power, sometimes we may be looking for the cost of operating something throughout a certain period of time. Well, how do we find that out? Well, our cost of operating something is equal to the price multiplied by the energy. So this is where this formula here can come important. And another really key part about working with electrical energy, when you're looking at electrical meters, if you're measuring like the energy in your house or the energy usage in your house, you're often going to be using kilowatts per hour as your units. So you're trying to measure how much energy there's going in throughout your house or over a certain amount of time. We'll actually look at an example problem here, and we'll talk more about how this is really used. But really, like, you'll have a kilowatts hour measurement on a lot of your things inside your house that can really tell you the efficiency too. Even in Ontario, you'll have Enron. We have Enbridge down here that supplies us power. All these things we can look for, and we can look for their electrical voltage, their electrical powers, their efficiency. All these things are really public. Now, you can really just apply from our physics to our real life. But let's go down here and let's take a look at this sample problem. So let's get into our given. So what is the cost of operating a 25-watt light bulb for 4 hours a day for 66 days? This should be 6 days, for 6.0 days. If the price of the electrical energy is 5 cents per kilowatt hour. Well, to do this, let's first get that our given. So it says, what is the cost of operating a 25 kilowatt watt light bulb? Well, if we know that by the unit that this is actually going to be power, because the units for power are watts. So 25 watts, that's what it is. So our time here, our delta T, is equal to 4 hours, but this is per day. So we know that it's going to be over a course of 6 days. So we can multiply this just by 6.0 days, and we'll get how many hours in total, because we're going to be operating it 4 hours in 6 days. So it's really 4 times 6, and our delta T will just equal 24 hours. If you really wanted to, you could have done this for 66 days, like I had the typo, and you would have got the same result. Really flow or process is what I'm looking for. That's what I'm looking for. You'd have the same process in the end. But let's keep going. So our delta T is going to be 24 hours in total. So it says if the price of energy is 5 cents per kilowatt hour. So our cost is equal to 5 cents per kilowatt hour. So let's go into our required to find. We're looking for really what is the cost, right? So we're looking for what is the total cost. So total over this period of time. So let's go into our analysis. Well, we know that we have our formula for, we have power, we have time, and we know that the cost is going to equal to price times energy. This is mislabeled. This should really be labeled as the price. It's not the cost, pardon me. This is really the price of doing it. So now that we have that, we're looking for the total cost. So we know that the cost is going to be price times energy, but we don't have energy. So what do we have? We have delta E is equal to P times delta T. Well, now that we have this formula here, from here it's simple to get energy, because energy we just multiply by, we just multiply our power by our time, which is in hours. Remember, we want to keep everything the same units. If we multiply watts by hours, we'll get a watt times an hour, and then we move it to kilowatt hours, which I'll show you in a second though. So we know that this is going to be our answer for there. So we can go into our solution right away. We can go delta E is equal to 25 watts multiplied by time, which is 24 hours. Hours and watts just become watt hour, or that's pretty much just the unit for them. And then you can just go 25 times 24, and you end up getting 600 watt hour. And then if we want to get this into kilowatts an hour, we just divide by 1,000, because this is right now just in standard. But if we want to get kilowatts an hour, which is the unit that we want to use, and which is the unit we use here, just divide by 1,000. So 0.60 kilowatts an hour. Now that we have that, we want to get the price. So the price, or our cost really, our cost is equal to the price, which is 5 cents per kilowatt. Pardon me. 5 cents per kilowatt hour. And we want to multiply that by the energy, which is 0.60 kilowatts an hour. Kilowatts will cancel out. You're left with cents on top. So if it says 5 cents, remember we want to convert this. We don't want to leave it as just 5. We want to convert it into 0.05. Why do we do that? Because in a dollar, there's 100 cents. So if we have 5 cents, we really want to keep all the units the same. So we can go cost is equal to 0.05. We can put dollars now, really. Multiply by 0.60 kilowatts an hour. And you can put kilowatts here, but kilowatts already canceled out. And now you get 0.05 times 0.60. And your final answer should be, your cost is 0.03 dollars. So that is basically your total cost. So that's how you determine what your cost is when you're doing these type of questions. Really just remember that it's all about manipulating the formulas again, and make sure all your units match up, because right now we found it what it is in dollars, what the cost will be in dollars. So if you want, you can convert to cents. It really doesn't matter. It's all up to you, but you can put your unit for dollars right there. And that's basically what power is and how it's applicable to our questions in this course. In the next video, we'll be talking about warmth and coldness, and the next section, the next unit in this course. So I hope you enjoyed, and remember, physics rocks.